Welcome everyone. For today's prep, we're going to see how to find absolute extrema. And the method we're going to be using is called the closed interval method. So first of all, we're going to see, the definitions for absolute max and min. And we'll look at those a little more in class as well. And we're going to be able to find the absolute max and min using a closed interval method. And first, let's look at our definitions. So what we've been working with so far with our first derivative test and our second derivative test is locating what we call local maxes and local mins, or relative maxes and relative mins. And these are places on our graph where we have a high point or a low point. And kind of the key word here for local is, or the key word here is local. And what we're talking about is x values that are close to our critical number. So a local max is a function value that's bigger than all of the surrounding function values for x that's kind of close to our critical number. And then local min is kind of the same thing. So it's a minimum, it's a value of our function that's smaller than all of the surrounding function values. So for inputs that are close to our critical number. And what we're going to be looking at now is what we call absolute max and absolute min. So the difference here with absolute is that we're not just looking at x close to our critical number, we're looking at all x in the domain of our function. So when we think of a local max, you want to think of this as like a mountain peak. And so, in a mountain range, there's a whole bunch of different mountain peaks. So there's high points and low points on a graph of a function. So a local max is just one of the high points along our graph. There might be other high points that are higher than it, but this is just one of our places on our graph that's higher than all of the surrounding values. What the absolute max is, this is the highest point on our graph. So you can think of this like the absolute max is like the Mount Everest of mountain peaks. Sure, there's other mountain peaks out there, but Mount Everest is the tallest one. So that would be like our absolute max. So that's what we're looking at when we talk about absolute max and absolute min, is it's a high point, but it's the highest point, or it's the lowest point on our graph. All right, so we have a result here called the extreme value theorem. And what this extreme value theorem says is if we have some conditions on our function is guaranteed to have an absolute max and min. So what we need is we need our function to be continuous, and we're going to be looking at a closed interval. So the closed interval means we have the endpoints. We're considering the endpoints. So we use square brackets for closed interval. So the first graph here, this is an example of a continuous function, and we're looking at just a closed interval. And we can tell that because we have the endpoints on our curve. So in this example, what we have is our function is continuous, and we have a closed interval. And we can tell our function's continuous because there's no jumps or breaks in it. And we know we're looking at just a closed interval because it contains the left endpoint and the right endpoint here. So that would technically be along the x-axis, but if we follow up, we've got the endpoints on our curve. Okay, so if these two conditions are satisfied, then what this theorem says is it guarantees that we should have an absolute max and an absolute min. So for this one, if we're looking for the highest point on our graph, we see that this is the highest point. So this is our absolute max point. And for the absolute min, if we're looking on our graph, we want to see what is the lowest point. So that's this one right here. That's going to be our absolute min. So the way we write this out is this graph has an absolute max value. And the max value in this case is the y-coordinate of 6. And we know that this max value happens at x equals 8. So the value of our function is 6, and the x value where this happens is x equals 8. And then we'd also write out that the absolute min value is equal to 1, and we know that that happens at x equals 6. So the y-coordinate's the function value. The x-coordinate is where it happens. So what we're seeing here is we're seeing that our absolute min is happening at one of our critical numbers, and the absolute max is happening at one of the endpoints. And so this gives us kind of an idea for how to go about locating where our function has an absolute max and an absolute min. And we'll look at these other two graphs in class, but these are examples where we don't necessarily have an absolute max or min, and that's because one of these two conditions is not true in either of those. So we'll look at those in class. But what's our strategy going to be for how to locate absolute extreme points? Well, if they exist, and we know that if we're looking at a closed interval, and our function's continuous, then they will exist. What we know is that it can happen at either the critical numbers or the endpoints. So the critical points, the critical numbers, that's where our function could have a local max or min, and then we've also seen that it can happen at the endpoints. So our strategy we call the closed interval method. And what we're going to do is we're going to first just verify that those two conditions are satisfied. So our function f is continuous on the closed interval from a to b. And then once we've verified those two conditions, then we're going to figure out the critical numbers of our function that sit inside the interval. So just a little warning there. Only use critical numbers inside the interval. So sometimes we might have an interval and we find critical numbers that sit outside the interval. So we would throw those out. We wouldn't use them. So we're only interested in the critical numbers that sit inside this interval. And then once we find those critical numbers, we're going to plug into our function the endpoints and those critical numbers, and then we're just going to compare. So whichever one is the largest value, that's going to be our absolute max, and whichever one is the, little typo here, whichever is the smallest value, that's going to be our absolute min. So let's try an example of this. Let's look at example 1. So we're going to find the absolute max and min values for this polynomial, x cubed plus 3x squared minus 9x minus 7. And we are dealing with a closed interval here, so square brackets means we're including the endpoints. So let's start. First step, let's just verify the conditions. So what do we need? Well, we need f to be continuous. So is this function continuous? Yeah, it's a polynomial. So polynomials are continuous. There's no division by 0 or anything, so no issues there. What else do we need? Well, we're also looking at a closed interval. So we need both of those. So is this a closed interval? Yeah. -6 to 4, square brackets on both sides. We're including both endpoints. So, yep, that's a closed interval. So once we verified both of those conditions are satisfied, then the next step is to find the critical numbers for our function. So that's the next step. Let's get the critical numbers. All right, so how do we get the critical numbers? Well, we've been practicing this. This is where we calculate our first derivative, and we look for where the first derivative is either 0, or the other option is the first derivative being undefined. So we're looking for either of those. And if we look at our, well, let's calculate our first derivative first. So we need our first derivative to help us out. And just a polynomial, so we'll just go term by term to differentiate everything. So we get 3x squared plus 6x minus 9. And then usually a good idea, try to factor right away. Now, the number in front of the x squared here is a 3, so it helps to try to factor off that 3. And just so happens we have a 3 in common with all those other constants. So start by factoring out the 3. And then, once you have that factored out, try to finish factoring here. So this factors nicely into x plus 3 and x minus 1. Okay. So we got it all nice and factored. If we look at our derivative, there's no division by 0 or negative exponents. So we're not going to run into any issue here. So that we're not going to get a critical number from the derivative being undefined. And we have this all nice and factored. So trying to figure out where this derivative is equal to 0, we can just set each of these factors to 0. And we only have to worry about the variable factors. So we can set x plus 3 and x minus 1, set both of those to 0. This constant factor, we don't really have to worry about because this can't make our derivative equal to 0. Only these variable ones. Those are the only factors that can make it 0. So if we solve each of those equations for x, we get x equal to negative 3 and x equal to 1. So we find our critical numbers. And at this point, it's just a good idea, double check, are these critical numbers actually in the interval? So at this point, you just want to double check. Are they in the interval? And in this case, yeah, negative 3 is definitely in between negative 6 and 4, and x equals 1, also in there. If we had found that, say, this was negative 8, well then we would throw negative 8 is not inside that interval, so we would throw that one out. So it's a perfectly good critical number for that entire function, but we're looking at just a section on this closed interval. Okay, so both of these are. So now the next step is to evaluate this function. And we're going to plug in the two critical numbers that we found and also the two endpoints. So we got to do two things. We got to evaluate the critical numbers. And then also the endpoints. So we want to do both. And we're doing the original function. Not the derivative or anything like that. We're doing our original. Okay. So let's see. We're going to take, what were the two critical numbers? They were negative 3 and positive 1. So we're going to plug each of those into our function, the original function. And then the two endpoints of our closed interval, negative 6 and 4, we're going to plug those in. And the idea here is we're just going to evaluate our original function at each of these numbers, and whichever one is the biggest value, that's going to be our max, and whichever one is the smallest, that's going to be our min. So let's try out. For negative 3, let's plug negative 3 into this function. And when we do that, we get negative 3 cubed plus 3 times negative 3 squared minus 9 times negative 3 minus 7. And I think if we simplify that, I think this is negative 27, this is positive 27. So those cancel. And then we have positive 27 minus 7. So we end up with 20. If we do 1, plug 1 in. So powers of 1 are just 1. So we end up with 1 plus 3 minus 9 minus 7, and that ends up being negative 12 if we simplify. And then negative 6 we plug in. So with negative numbers, it's helpful to use parentheses. So we get negative 6 cubed plus 3 times negative 6 squared minus 9 times negative 6 minus 7. And if we simplify that, we get negative 61. And I'm looking. I'm cheating. So negative 61. And then for x equals 4, same thing. We're just plugging it into the function. So and in this case, 4 cubed plus 3 times 4 squared minus 9 times 4 minus 7. And this ends up being 69. All right, so what we have here is a list of 4 function values. And the idea for our last step is just to compare these. So we just want to pick out which one of these values is the largest and which one is the smallest. So in this case, the largest value, if we scan through our list, the largest value is 69. So that's going to be our absolute max. So we know our absolute max value is 69, and this occurs at x equals 4. And then we just scan through the list and we look for the smallest of those 4 values. And we see that that is negative 61. So the absolute, not max, min value is going to be negative 61. And that happens at x equals negative 6. So this is our absolute min, and that's our absolute max. And that's the idea with the closed interval method. So the kind of the classifying of our critical numbers in this case and the endpoints is we can do it by just evaluating the function. All right, so we'll try another example like this in class, but this method for finding the absolute max and min when we're looking at a closed interval is called the closed interval method. So we'll see you in class. Bye-bye.